In this video, we are going to look at the problems on the 11.5 slides. We're starting here where we're asked to find the expected number of boys for a 3-child family. That is, we want to know the expected value of the number of boys, assume boys and girls are equally likely. So the first thing we want to do is we want to set up a table with the number of boys and the probabilities accompanied. So, you know, we can start with this. We've got and the probability and the product, because we're going to multiply those two things together. Okay, so when there are 0 boys, that happens 1/8 of the time, and the product of 0 and anything is 0. When there is 1 boy, that's going to happen 3/8 of the time. We've seen that before, and the product of 1 and 3/8 is still 3/8. When there are 2 boys, that will also happen 3/8 of the time. So 2 plus 3/8 is 6/8. And when there are 3 boys, that will happen 1/8 of the time. And the sum there is going to be 3/8 again. Then the expected value is equal to the sum of this column. 0 plus 3/8 plus 6/8, that's 9/8. 9/8 plus 3/8 is 12/8. But 12/8 is 1.5. So our expected value is 1.5 boys in a 3-child family, which basically means there are 1 or 2. It's certainly more likely to get 1 or 2 than it is to get 3. A player pays $3 to play this game. He tosses 3 fair coins and receives back payoff of $1 if he tosses no heads, $2 for 1 head, $3 for 2 heads, and $4 for 3 heads. Find the player's expected net winnings for this game. Okay, well, again, we set up our table. Here is the payoff for, you got the payoff, the probability of the payoff, which is just going to be the probability of having that particular number of heads, and the product. Okay, so the payoff for 0 heads is $1. The probability of 0 heads is 1/8. Yes, because we're dealing with 3 fair coins. We're dealing with those 8ths again. The product of these numbers is 1/8. Payoff is $2 for 1 head, and there is a 3/8 probability of 2 heads, of 1 head, so that is a product of 6/8. Payoff is $3 for 2 heads. Again, we have a 3/8 probability for 2 heads, so the probability is, so the product is going to be 9/8. And finally, the payoff is $4 for 3 heads, but the probability of 3 heads is 1/8. So that's going to be a total of 8/8 here. Okay, so when we add all of these up, 1/8 plus 6/8 plus 9/8 plus 8/8. Okay, 1/8 plus 6/8 is 7/8, plus 9/8 is 16/8, which is 2. And plus 8/8, that gives us 3. So our expected net winnings for the game are $3. Our expected winnings for the game are $3. However, The net winnings means we have to take away the $3 that we initially spent. So we have an expected net winnings of 0. And that makes this a fair game. We'd rather make money, but as long as we break even, it's a fair game. And something I did wrong. What did I do wrong? Sorry. Oh, I see. You're supposed to do it this a little differently. I apologize. Messed this one up. The actual way that we're supposed to handle this is to subtract our payoff from our we have to figure out our net winnings. So for 0 heads, we got $1, but we lost $2 in the process because we paid 3. So we take that 1/8 and multiply it by the -2 and get -2/8. And then we do the same for 1. Well, we get $2 for that, but that means we have a net winning of -$1. Probability is 3/8, so that's -3/8. For 2 heads, we'd win $3. Net winnings are 0. 3/8, 0. And for 4 heads, that's we win $4. Net winnings $1. 1/8. 1/8 times 1 is 1/8. We add those up. -2/8 plus 3/8 minus 3/8 is -5/8 plus 1/8 is -4/8, or -50 cents. So that is our actual net winnings, expected net winnings. Sorry about the confusion there. Moving on. $3 cost to pay the game. In the last example, made the game unfair against the player. What would make this a fair game? Well, the thing here is that because we had a 50-cent, since the net winnings, the expected net winnings are -50 cents, that means that the price is 50 cents too high. So we just need to decrease the price of our $3 game by 50 cents to get $2.50 for the fair game. In a certain state lottery, a player chooses 3 digits in a specific order. Leading digits may be 0, so numbers such as 028 and 003 are legitimate entries. The lottery operators randomly select a 3-digit sequence, and any player matching that selection receives a payoff of $600. What is a fair cost to play this game? Okay, well, they're paying, it doesn't tell us what they're paying. We just need to figure out what the expected value of this game is. There are 1,000 different combinations, and one of them is going to give us 600, and the rest of them are going to give us nothing. So we've got 1 times 600 plus 0 times every other number, or times 999. Well, that leaves us 600, but And then we need to divide this by 1,000. This is really 1 over 1,000 times 600 plus 0 times 999 over 1,000. And that's going to give us 60 cents. And that 60 cents is the fair price to play the game. One simple type of roulette is played with an ivory ball and a wheel set in motion. The wheel contains 38 compartments. 18 of the compartments are black, 18 are red, and 2 labeled 0 and 00 are green. Assume the player places $1 on red or black. If the player picks the correct color of the compartment in which the ball lands, the payoff is $2. Otherwise, the payoff is 0. Find the expected net winnings. So the expected net winnings are this. If you guessed correctly, you get an extra $1. And that can happen 18 out of 38 times. If you guess incorrectly, you lose $1. And that can happen 20 out of 38 times. This, of course, assumes you don't bet on green because green comes up, only 2 out of 38 times. It's generally a bad bet. When we simplify this, well, 18 out of 38 is the same as 9 out of 19. 20 out of 38 is the same as 10 out of 19. So we've got 9/18 minus 10/18. Your expected value is negative 1/19 of $1. So a little more than 5 cents. About 5.3 cents. If somebody is to invest $5,000 in one of these stocks, which offers the highest expected profit? Okay, well, to figure this out, we just say what's going to happen. We've got our profits all figured out. We've got probabilities for each of the profits. We just calculate it this way. I do 0.2 times negative 400 plus 0.5 times 800 plus 0.3 times 1500. Okay, well, I add that all up. 0.2 times negative 400 is negative 80 plus 0.5 times 800 is 400 plus 0.3 times 1500 is what, 450? Yes. Okay, so for company ABC, the potential profit or the expected profit is going to be $770. We do the same thing for RST here. We take our profit and multiply it by our probability. 500 times 0.8 plus 1,000 times 0.2. Okay, 500 times 0.8 gives us 400 plus 1,000 times 0.2 gives us 200 for a total of $600 in expected profit. Finally, here we are, we've got company XYZ. 0 times 0.4 is 0, so we're not going to worry about multiplying that out. But 0.3 times 700 plus 0.1 times 1200 plus 0.2 times 2000. That we can set up. Okay, so 0.3 times 700 is 210 plus 0.1 times 1200 is 120 plus 0.2 times 2000 is 800. That leaves us 210 plus 120 is 330 plus 800 is 1130. So clearly the I did something wrong there. 0.2 times 2000 is 400, not, yeah, that should be 400, not 800. So that should be 730 there. So clearly, if we're going entirely on the basis of expected value, the investor should choose company ABC. Next question relates to that one. If in the previous example, which stock should an investor choose if they're an optimist or if they're a pessimist? Well, an optimist focuses only on the best outcome, and the best outcome was getting $2,000 for company XYZ. Pessimist focuses on the least of the worst outcomes. The least of the worst outcomes was getting $500 investing in company RST. Okay, so I have people gathering for my next class, and I will finish up this video when I have time.